Okay, let's talk about something we all kind of take for granted. The electron. You know, that tiny little particle? Well, it turns out it's hiding one of the biggest, most mind-bending mysteries in the entire universe.
And that mystery is, why are they all exactly the same? I mean, perfectly identical. It's not like they're just similar, like two cars off an assembly line. Nope. Every single electron is a flawless, perfect clone of every other one. So, why?
And you have to understand, there are a lot of them. We're talking about a number so big it's hard to even write down. Roughly 1 with 80 zeros after it. That is an absolutely insane number of perfect, identical copies. This can't be a coincidence, right? There's no way.
And that's the key right there. This isn't just some boring fact you memorize in physics class. This perfect uniformity, it's a clue. A massive clue that's pointing us towards a reality that is way, way stranger than you could possibly imagine.
So, you've got this cosmic identity crisis, right? This completely bizarre fact that all these particles are perfect clones. Well, this puzzle led one physicist to have an idea so wild, so out there, but so brilliant, it was about to change everything we thought we knew. That physicist was John Wheeler, and he picks up the phone to call his grad student, a young Richard Feynman. And he says, "Feynman, I know why all electrons have the same charge and the same mass. Because they are all the same electron." Just imagine getting that call. The idea is so simple it's genius, and it's also completely bonkers. They're all identical because they are literally the same one. Yeah, just let that sink in for a second. What if the electron in the tip of your finger and an electron in a star on the other side of the galaxy are just two different appearances of the exact same particle? But hold on. How on earth can one thing be in a bazillion places at the same time?
Well, here's how the idea works. Imagine all of space-time. That's all of space and all of time, from the Big Bang to the end of the universe, as one giant block. Now, this single electron isn't just a dot in that block. It's an incredibly long, tangled-up thread weaving its way all through it. In our present moment, that's just one thin slice of the block. When we look at that slice, we see the thread poking through in billions and billions of places, and we think, hey, look at all those different electrons. But we're wrong. It's all just one thread.
So it's kind of like one actor playing every single part in a giant cosmic movie. To us, it looks like a cast of trillions, but nope, it's just the same actor showing up over and over again. Okay, but this whole one-thread idea still has a problem. What about antimatter? What about the electron's opposite, the positron? Well, the theory has a ridiculously cool answer for that, and it involves one of my favorite concepts, time travel. Okay, this is where it gets really wild. For this whole thing to work, that long thread, the electron's path through spacetime, can't just move forward in time. It has to be able to whip around and start traveling backward in time. Now, this isn't just some made-up story. There's a real concept in physics for this. It's called the Feynman-Stueckelberg interpretation. And what it basically says is that mathematically, an antiparticle, like a positron, is completely identical to its regular particle counterpart, just traveling backward in time. Think about it like this. An electron zipping forward in time has a negative charge. But when that exact same particle does a U-turn and starts moving backward in time, we see it as something totally different. We see it as a positron with a positive charge. They're literally two sides of the same coin, just heading in opposite directions through time. This completely changes how we think about things like particle annihilation. You know, when an electron and a positron meet and disappear. In this picture, that's just the single electron hitting a kink in its path and making a U-turn in time. It switches from moving forward to moving backward. And pair creation, that's just the electron making a U-turn from the past into the future. It's not really creation or destruction, it's just a time travel U-turn. And I know this sounds like something straight out of science fiction, but the math behind it, it works. It works perfectly. This whole idea of treating antimatter as matter going back in time became a huge deal in physics. But for the grand vision, the one-electron universe, there's a catch. A really big one. You know, a beautiful theory is a wonderful thing, but at the end of the day, it has to match reality. It has to match what we actually see out there. And this is where this elegant, mind-blowing idea hits a brick wall, hard. This was actually Feynman's first question to Wheeler. He said, wait a minute, if it's just one particle zigzagging through time, then for every part of the line moving forward, there should be another part moving backward. That means the number of electrons and positrons in the universe should be pretty much equal. But they're not even close. I mean, just look around. Everything you see,
everything we've ever observed in the cosmos is overwhelmingly made of matter. Electrons are everywhere. They're a fundamental part of you and me. But positrons? They're antimatter twins? They are ridiculously, unbelievably rare.
This massive imbalance between matter and antimatter is, funnily enough, another one of the biggest unsolved mysteries in all of physics. And for the one-electron universe theory, it's a fatal blow. It just doesn't match what we see. So, was it all just a beautiful idea that failed? Well, no, not at all, actually. Because even though the grand vision, this idea of a single electron literally being everything, didn't pan out, a core piece of it, a truly crucial part of the puzzle, was spectacularly right. And that one piece would go on to change physics forever.
And you don't have to take my word for it. Here's Feynman himself talking about it. He basically said, look, I didn't take the whole all electrons are the same one idea seriously, but the part about positrons being electrons going from the future to the past, that I stole. He knew genius when he saw it, and he wasn't about to let it go.
And what did he do with that stolen idea? He used it to create Feynman diagrams. These are literally the pictures that physicists use to figure out everything that happens in the quantum world. If you ever see one, an arrow pointing forward in time represents a particle, and an arrow pointing backward in time, that's its antiparticle. It's simple, it's powerful, and it all started with that one crazy phone call.
You know what I love about this story is how Feynman later talked about Wheeler. He said his own mind was fertile soil for Wheeler's wildness. He was willing to listen to a crazy idea that other people would have just dismissed immediately. And it's such a perfect example of how science really moves forward. It's not just about cold, hard facts. It's about creativity, imagination, and being open to the wild ideas.
So, that leaves us with a really cool thought to chew on. The one-electron universe theory was, in the end, wrong. But a piece of it was so right that it changed everything. It really makes you wonder, doesn't it? How many other beautiful, wrong ideas are floating around out there right now, just waiting for the right person to find the piece of truth hidden inside?